Good morning. Welcome to tutorial 7. This is on psychrometric processes. The first problem, air at 30 degrees and 100 kilopascals. So we can say T1 equal to 30 degrees and the total pressure is 100 kilopascals. Is observed to have a dew point temperature of 20 degrees. So we have to find the relative humidity, partial pressure of the dry air and the humidity ratio. Okay, now consider this TS diagram. Let PV be the partial pressure of water vapor. So obviously we are considering this air as the moisture air, which has dry air plus water vapor. The total pressure of this mixture of dry air and water vapor is 100 kilopascals. The PV is the partial pressure of the water vapor present in the air. So now the state is represented in the TS diagram like this, in which PV isobar is shown and state 1 is corresponding to temperature 30 degrees, it is superheated state. Now dew point is given as 20 degrees. That means if from state 1 I cool this in constant pressure process, I will reach the saturated vapor state. So this is called dew point temperature. Obviously that will be equal to T sat at PV. So now we know that the dew point temperature TdP equal to T sat at PV, which is actually given as 20 degrees centigrade. So from which I can find PV. So if you go to tables, okay, if you go to from saturated steam tables corresponding to 20 degrees centigrade, P sat will be equal to 2.34 kilopascals. So this will be equal to PV. So PV will be equal to P sat at dew point, that is 20 degrees centigrade, that is equal to 2.34 kilopascals. Okay, now what is relative humidity? Phi. Relative humidity will be equal to PV divided by P sat at the given temperature T. What is the given temperature? That is 30 degrees. So that will be equal to 2.34 divided by P sat at 30 degrees centigrade. So again from the saturated steam table corresponding to 30 degrees, I can get this value, that will be equal to 2.34 divided by 4.25. So the relative humidity comes out as 0.5506 or 55%. So this is about the relative humidity, which is nothing but the partial pressure of the water vapor divided by the pressure at which the air is saturated at the given temperature T. So this is we are talking about this pressure when I go to this state, correct? So this is one, this is dew point, and this is the saturated state. Yes, I can say, so saturated state. So I will find this pressure. For example, this will be the P sat at 30 degrees. Okay, so that I substitute here and get the value of phi. Then what is asked? So we have calculated the relative humidity. Then partial pressure of dry air. Partial pressure of dry air will be equal to total pressure minus partial pressure of the water vapor. That will be equal to 100 kilopascals minus this is 2.34. So that will be equal to 97.66 kilopascals. Then we want specific humidity, that is humidity ratio or specific humidity. which will be equal to 0.622 into PV by PA. So when you substitute these values, you will get 0.0149 kg vapor divided by kg of dry air. That will be the value. So you can see that by simple calculation, we need steam tables to find the, for example, here the saturation pressure corresponding to dew point, which is given, and the saturation pressure corresponding to 30 degrees, which is the given temperature, have to be retrieved from the steam tables. Then we can do this calculation. On the other hand, we can also do this by using a psychrometric chart. So note that the dry bulb temperature is 30 degrees and dew point is 20 degrees. Okay, now one point is, if the pressure is 1 atmosphere or 1 bar, okay, which are close to each other, then only psychrometric chart can be used, or we have to calibrate a chart or make a chart which is for the different pressure. Normally the psychrometric chart which is available is will have the data for corresponding to 1 atmospheric pressure, or you can say 100 kilopascals. So a typical psychrometric chart looks like this. You know this. So the x-axis is the dry bulb temperature and the y-axis is the, you have several points here. So you can dew point, you can see here, humidity ratio will be there, and so on, and a lot of other scales are there in this. So enthalpy, then saturation temperature, and there are curves for phi, that is relative humidity, etc. Okay. Now we have to go to the state 1, which is fixed by the temperature, which is dry bulb temperature is 30 degrees, that is given, and second point is the dew point, which is 20 degrees. So dew point 20 degrees and the dry bulb temperature 30 degrees. So your point comes somewhere here. So dew point here and the 30 degrees is somewhere here. Go and fix the state here. It will be here. Okay. Yeah, here. So now you can see that so this will be the state 1. Now from this you can retrieve other values. So corresponding to the state, I can retrieve the values. For example, now relative humidity. This is the 50% relative humidity and this is 60% relative humidity. So this is in between these two. So I can say 55%. That's what we have calculated. Okay. Correct. So this is 50% relative humidity line and this is 60% relative humidity line. This is almost in the center of these two. So I can say phi for this is 55%. Similarly, omega is here the humidity ratio. So from this point you can go to this scale and fix this value. This is 10, 11, 12, 13, 14. So this is 14.5 something. So what we have calculated is about 14.9. So that is what we are getting. So even though in one shot, by just fixing the state with two properties, I can find all other variables properties. For example, here enthalpy also can be found. From this scale, I can say the enthalpy will be 65, 66, 67, 68. So it is approximately 60, 66 kilojoule per kg of dry air. So all other properties I can retrieve. Okay. Only thing is you have to accurately go and mark the state, and correspondingly you have to use a scale and actually get the states. Okay. Calculation takes several steps, but in one shot we can get. But one point to remember is this is calibrated for 1 atmospheric pressure. Okay, it's clearly given 760 mm of mercury. We need several charts, okay, where different pressures can be used, but it is very tedious to make such a chart for different pressures. But normally the applications for psychrometric processes, we will have the total pressure very close to 1 atmosphere, so we can use the chart. Okay, so this is about the problem 1. Simple, how to use a given state and go to find the other properties. The second, air is stored in a tank of volume 50 meter cube, pressure is 0.1 megapascals and temperature is 30 with relative humidity of 80%. So determine the mass of dry air, specific humidity and dew point temperature. Okay, so we will first do it using the equations. Equations means you need what? You need the steam tables to retrieve the values. Okay, for example, the partial pressures, etc. Then you have expressions from which you can calculate the relative humidity, specific humidity, and so on. So in this problem, we have T1 equal to 30 degrees centigrade, then Phi1 equal to 80%, that is 0.8. Then so this will be equal to what? So PV1 divided by Psat at the given temperature, that is 30 degrees centigrade. So that implies PV1 will be equal to 0.8 into Psat at 30 degrees is 4.25 kilopascals. So I get this as 3.4 kilopascals. Okay, now what will be the pressure of air? Pressure of air will be equal to the total pressure minus the partial pressure of the water vapor. That will be actually 100 kilopascals. So 0.2 megapascals is 100 kilopascals minus 3.4. So that will be equal to 96.6 kilopascals. So now for air, I can say, or the specific gas constant is 287 joule per kg Kelvin. So with that, I can find the density of the air, correct? Or the mass of the air you can straight away find using the equation of state. So that will be equal to Ma equal to mass of the air will be equal to 96.6. Please understand this is partial pressure of air that should be used. So convert into pascals into the volume is given as 50 meter cube divided by 287 is the specific gas constant. If temperature is 30 degrees, that is 273 plus 30. So when you substitute, I get the mass as 55.54 kg. So bigger, very big drum. So we have very good mass of the dry air here. Now that is done. Then specific humidity omega will be equal to 0.622 into PV1 by PA1. We know these values. Substituting point, we get 0.02189 kg vapor divided by kg dry air. Okay. So in the psychometry chart, you will get gram instead of kg. You will get grams basically. So now dew point temperature. Dew point temperature is nothing but the saturation temperature at the partial pressure, correct? So we know this, correct? So this is the initially the air is in superheated state. So this will be state 1. So this is PV and this will be the temperature, say 30 degrees centigrade, and this is PV equal to, we can say 3.4 kilopascals. So now this is the dew point. So that is the saturation temperature at PV1, Tsat at PV1. So now that will be equal to, again you have to go to steam tables for retrieving the Psat and Tsat, etc. I have to go to steam tables and refer that. So here we can take the interpolate and get the value of this about 25.5 degrees centigrade. So this again I can do this using the psychrometric chart. What properties I will use? T1, the dry bulb temperature, that is 30, relative humidity 80. So these two properties will fix the state. So going to the psychrometric chart, I first erase the previous entries. So now I have relative humidity 80%. So this line, and 30 degrees. So 30 degrees is this line, and relative humidity of 80% tells here this something here it will get, okay. So you have to use scales. If you use scales, it will be very accurate basically. Okay, so this is 30 degrees, correct, and this is the 80%. So this is the state. So once the state is fixed, I can find any other property I want. For example, I go in this scale and find the humidity ratio, which is 20. Here you can see this 20, 21 plus 22, it is about 21.8 grams. So what we have calculated is 21.89 grams. So it is fine, correct. So humidity ratio. Then you can find the uh, density of the gas. So specific volume of dry air is given. So that you can these are the lines in that. So you can take that. It is between 0.9 meter cube per kg and 0.88 meter per kg. So I can say it is 0.89 meter cube per kg. Okay. So from that I can find the density. Okay. Mass is density into volume. Volume is 50 meter cube is given. So it is about 0.88 and 0.9 average of these two. Okay. Or you can also interpolate if you want, you can carefully interpolate also and get the value. So let us approximately take it as 0.89, that is the specific volume, that into mass can be calculated by volume by the specific volume, that is 50 meter cube by 0.89. So that in that way we can find the mass. So once you fix the state, I can find any other values also. Here enthalpy also can be found. This enthalpy of dry, the enthalpy of the moisture is given. That is actually H star. Okay, that will be equal to H air plus HV into omega. Okay, so now this can be written as Cp into T plus omega into Hg. Now this T actually in this scale it is in degree centigrade, and Hg is the saturated vapors enthalpy at the given temperature T. So that is what is given here. So if you multiply by the mass of dry air, you will get the total enthalpy. Okay, so this is about this chart. So this is about this problem where you can see that in a simple manner we can calculate. Only by steam tables you can do this calculation. More accurate values will be got. But if you use the chart, you have to be very careful in actually interpolating between this, because you have to actually divide, put a scale perpendicular and see what are the number of divisions and where the particular point comes. So how to basically by pixels you have to slightly interpolate and get. It's slightly tedious, but approximate values can be very easily taken in one shot. In some problems, we have to really use the chart only. It is very easy to do that, or else you have to end up in an iterative procedure. Then the third problem. Now this problem involves a lot of calculations. Let us go through this carefully. A system contains 10 grams of liquid water and an ideal gas mixture of air and water vapor at a pressure of 360 kilopascals. So now straight away pressure is 360 kilopascals. It's not around the atmospheric pressure of 1 atmosphere. So for this problem we will not be able to use the psychrometric chart. Okay, and temperature is 25 degrees. So, okay, now please see, I am talking about some volume like this, in which some water is there, 10 grams of water. This is a liquid state. Then there is a gas mixture which is actually air plus water vapor. The total mass is 1 kg, that is given. Now the contents are gradually heated, slowly it is heated, okay, at constant volume. So everything is rigid, constant volume, heating is happening such that the partial pressure of water vapor attains a value of 10 kilopascals. Obviously some amount of water will escape, correct, and reach the vapor, so that the partial pressure increases for this mixture. Some liquid may also be there. So, what it said is the partial pressure of the total pressure in the system will be the sum of partial pressure of dry air and partial pressure of water vapor, because the partial pressure exerted by the liquid water is neglected, can be neglected. So, I do not need to take that, because you can say incompressible, so it is neglected. In general, the solid and liquids present in the system along with vapors, partial pressure of solids and liquids will be neglected. Now, one more main thing is it is a very huge, maybe the container is very huge and so on. So, what we can assume is due to the heating process where the partial pressure increases, the total pressure, let the total pressure remain constant. Because the data is not given, so let us say P1 equal to 360 kilopascals equal to P2. Okay, because the vessel is very huge, some amount of heat is added and partial pressure 10 kilopascals compared to 360 kilopascals is nothing. So, even though the from initial value of some low partial pressure of water vapor, the partial pressure of water vapor now increases to only 10 kilopascals. So, that means that the partial pressure need not change much. So, the total pressure need not change much. So, we can say that the total pressure remains almost the same. So, that is one assumption we can make in this particular problem. So, now lot of things are asked. So, initial specific humidity, okay, then mass of air, initial mass of water vapor, then initial volume, which is the final volume also obviously, the final temperature, final relative humidity and final specific humidity. So, these are the things which we have to solve. Obviously, we will only use equations and steam tables for retrieving data, not the psychrometric chart, because the pressure is not 1 atmosphere. Solution of this is basically since a mixture of liquid, water and vapor are present, we can say that PV1 will be equal to Psat at 25 degrees centigrade. Already saturation is reached. See, if saturation is not reached, then the liquid water will be absorbed by the air. Okay. Now, liquid is present over which vapor is present. That means the vapor air water vapor mixture cannot take any more liquid. So, it is a saturation condition. So, I can say that the initial partial pressure of water vapor will be just Psat at 25. So, I will say PV1 will be equal to 3.17 kilopascals. Obviously, I am taking this value from the steam tables. Next, we will say at 25 degrees, I will retrieve the value of the specific volume of the saturated liquid as 0.001032 meter cube per kg and Vg equal to 43.36 meter cube per kg. So, saturated mixture. So, I am taking the Vf and Vg to calculate other quantities later. So, now basically what is asked, we will solve one by one. First, initial specific humidity, that is omega 1, which is equal to 0.622 into PV1 divided by PA1, which is equal to 0.622 into PV1 divided by P minus PV1. So, that you know P equal to 360 and okay, P1 minus P1. So, this is equal to, we know the all values, substituting this I get the value for omega 1 as 0.005525 kg vapor divided by kg dry air. So that is omega 1. Now proceeding to the next point, mass of liquid water is given as 10 grams, which is equal to 10 into 10 power minus 3 kg. Mass of gas mixture, that is air plus water vapor, that will be equal to m g equal to m a plus m b, that is mass of air plus mass of water vapor, that will be equal to total mass mt minus the mass of water. So this is the mass of water. So that will be equal to 1 minus 0.01 is equal to 0.99 kg. Okay, then what is mass of dry air? Mass of dry air, Ma, will be equal to, so this mass of the vapor, air plus water vapor is mg. Okay, so this we can write as Ma into 1 plus omega. Okay, so Ma1 I will say, Ma1 omega 1 I will say here. Ma now will be equal to what? 0.9, this is 99 divided by 1 plus omega 1. So omega 1 we calculated. So using this I get the value of 0.98456 kg. Understand? So how it is coming? Ma into 1 will be Ma, Ma into omega will be mv by the definition of omega, correct? So I get Ma into 1 plus omega 1. I know the value of omega 1. I know the value of mg, the total mass of the gas mixture. So from that I can calculate the mass of the dry air. This is the second one, B. Then C is mass of water vapor. That will be equal to Ma into omega 1. So that will be equal to 0.005439 kg. Because omega is we calculated 0.50055 here, 5525, that into 0.98456, that will give you this value. So that is the C. Then so now we will say we have to calculate the volume. Okay, so for that I use ideal gas mixture, P1 into Vg equal to Ma plus Mb into R mixture into T. So now R mixture is calculated as the sigma Yi Ri, so which is equal to 0.98456, that is the mass of the dry air divided by the total mass 0.99, that is the mass fraction, into for air it is 287, plus for the mass of the water vapor is 0.005439 divided by 0.99 into its R is 8314 by molecular weight is 18. So universal gas constant by this. So when I substitute this, I get as 287.96, a slight increase from 287. Okay, so from this I can calculate Vg as 0.23598 meter cube. Okay, so this is the volume occupied by the the air plus water vapor, that is a gas mixture. Okay, so air and water vapor mixture. So this is about the volume. This is the initial volume of the system. Okay, initial volume of the system is this plus the volume occupied by the water vapor plus air is 0.235. But what about the water? Volume occupied by liquid initially, liquid water initially will be equal to what? That will be the mass 10 grams into Vf, that will be equal to 0.00001003, which is negligible. Okay, very small. This is meter cube. Because water density is very high, so it occupies very low. So that means we will say the initial volume or the volume of the container will be equal to 0. Here I write this as 236 meter cube. So this is the D. Okay, so you can see that I can, how I get this, because I know that for the pressure of 360, basically I have retrieved the values or the temperature is given, no, 25 degrees. I retrieved the values here. So from that Vf and Vg, Vf into the mass will give you the liquid. So that is what I got. So liquid mass is negligible, and from the equation of state, because the mixture is ideal gas mixture, so I can use the ideal gas equation of state and find the Vg value. So this is about this. Then state 2 after heating. PV2 equal to 10 kilopascal, that is given. After heating, what happens? The partial pressure of water vapor increases to, initially it is basically less, and now it increases to basically 10 kilopascals. PV1 is 3.17 kilopascals. It is slightly increasing to 10 actually. So this is why we assume the total pressure to be constant. So with this small increase, the total pressure will not be altering much, given the total pressure is 360 kilopascals. So now at the initial state, okay, that is 25 degrees centigrade, what is x1? X1 will be equal to mass of water vapor divided by the mass of total mass of water vapor plus liquid water. I will say mass of water total, I will say empty. So that will be equal to here 0.005439 divided by the mass of water, liquid water is 0.01 kg plus mass of water vapor 0.005439. Okay, if you add that, the quality will come as 0.3523. So I will find the specific volume of water. This include what? The mixture of liquid water and water vapor. I will say VW will be equal to what? The quality is known. So I will say this will be equal to Vf plus x times Vg minus Vf. So that comes out as, so Vg is 43.36, Vf is 0.001032 meter cube per kg. So substituting the values, x is known here, this is x1 I will put. So that will come out as 15.275 meter cube per kg. So this is the volume, okay, specific volume of the water, liquid water and water vapor mixture. Now heating is done by constant volume. See the problem, if you see, heated at constant volume. Now this is a rigid vessel, mass is constant, volume is also constant. That means the specific volume has to remain constant. Okay. Heating of the system occurs at constant volume. So that means VW1 will be equal to VW2 equal to 15.275 meter cube per kg. Okay, now finally partial pressure of water vapor is 10 kilopascals, and I can say the specific for the water, specific volume of the water is 15.275 meter cube per kg. This I know. What is this state? Now I find that VW is greater than Vg at 10 kilopascals. So that means the state 2 is superheated state, superheated vapor state. Okay, now 10 kilopascals corresponding to 0.1 bar. Okay, superheated tables. Superheated tables. Okay, for the specific volume of for V equal to 15.275 meter cube per kg, I can find the temperature. Temperature is equal to 58.7 degree centigrade or 331.7 Kelvin. This you can take from the superheated table corresponding to 0.1 bar, where you have to interpolate for the specific volume of 15.275. Okay, so for example 50 degrees and 100 degrees, two entries may be there. So by interpolating I will get the temperature corresponding to the specific volume which remains constant at 15.275 meter cube per kg. We will get the temperature and other properties, whatever other properties what you can get. But anyway, this is what is asked. So this will be the temperature at the state 2, that is E. Then final. So actually this is interpreted between 55 degrees and 60 degrees in 0.1 bar table. Okay, now final phi, that is phi 2 equal to, finally I will get phi 2 equal to what? PV2 divided by P sat at T2. Now I know T2. So again you have to interpolate from the tables to find the pressure, saturation pressure at T2. So that you will get, this is 10 kilopascals, that when you interpolate from the temperature based tables, again between 55 and 60 degrees, something like that, you get the pressure as saturation pressure at 58.7 degrees is 18.85 kilopascals, but the partial pressure is 10 kilopascals. So you get the relative humidity at state 2 as 53%. This is actually F. Then G is nothing but the pressure of air at the state 2. So you know that this can be got as PA1 into T2 by T1, since the volume is constant. Correct. So now this will be equal to 360 minus 3.17. Please understand that I have to substitute air's partial pressure. So 360 is the total pressure, 3.71 is the PV1. That will give you the value of PA1 into T2. T2 is nothing but 331.7 divided by here it is 298 for T1. T1 is 25 degrees, T2 is 58.7 degrees, but the ratio you have to convert it into Kelvin. So I understand that these are in Kelvin. So that will be equal to basically the pressure of dry air at the exit state is 397.18 kilopascal. Then we can find omega. Omega 2 will be equal to 0.622 PV2 divided by PA2. I know these values, so it is 0.622 into PV2 is 10 divided by PA2 is 397.18. So that will be equal to 0.01566 kg vapor divided by kg dry air. So you can see that using the expressions and the steam tables, calculations are done for this problem, and a psychrometry chart cannot be used. And in this problem, we have a constant volume heating. There is rigid volume which is heated, so that already a saturated air water vapor mixture is present over a small liquid layer of 10 grams. Now, due to the addition of heat, some water vapor vaporizes and the temperature increases, so that it goes to from phi equal to 1, the relative humidity drops, so that additional air water vapor is taken in. So the liquid water evaporates and goes into the air, and relative humidity becomes 53%. Okay. So since the pressure is 360, we cannot use the psychrometric charts. For this problem, we have to use the formulas and the steam table.